great destroyer of matter, the creator of energy. It was only with the study of chemistry that man learned what really happens when something burns. Neither matter nor energy is created, and neither is destroyed. Instead, each is converted into other forms. But although smoke and flame have all the necessary matter and energy, they do not create a dream. In our world, there are events that happen in one direction only. There are laws that govern basic driving forces in the universe and that make ours an irreversible world. There are two factors that give direction to events. One is the mover of matter, energy. To understand energy's role in the irreversible world, we must know some of its forms and how they work, how man tries to predict and control nature's power. Most energy on Earth originates on our nearest star, the Sun, a gigantic nuclear reaction almost 100 million miles away. The Sun's heat powers the wind, moves water. Its light gives energy to plants to begin the food chain that feeds all life. Man's first way of using energy was to apply the strength of his own muscles. Simple tools increased the force and the length of the Stone Age hunter's arm. But differently shaped and weighted shafts of wood or metal can only do so much. The next step was to learn how to store energy and how to release it. Then came the discovery of another kind of stored energy, chemical energy. It could be converted not only into heat, as in fire, but also into the energy of motion. And besides chemical energy, stored in the bonds between atoms, there is energy in the atomic nucleus itself. Chemical energy gives man the power even to propel himself into space. But he is using up some of his traditional sources of power. There is a shortage of fossil fuels and of electricity. But energy demands keep growing. The paradox is that energy in itself is as abundant as it ever was. One of the basic laws of nature tells us that the total amount of energy in the universe is constant. Energy can neither be created nor destroyed, but only converted from one form to another. Now, man must make other sources of energy economical to use. The sun itself may be a part of the answer. Light can be converted into electricity and then into the energy of motion on Earth and in space. In a nuclear reactor, it is possible to harness the energy stored in the atomic nucleus. Here, nuclear energy is converted partly into heat to run steam turbines that produce electricity. In nuclear changes, some matter is converted into energy. In chemical changes, as in the burning of coal or wood, the total amounts of matter and of energy remain constant. The problem is, although energy is not destroyed, it eventually becomes unavailable for useful work. For example, what happens to the energy released when a gallon of gasoline is burned in a car's engine? About 20% is used to propel the car forward, to overcome friction with the road and with the air. Eventually, this energy, and all the rest, is converted into a form that ends up doing just one thing: increasing the disorderly, random motion of molecules in the car and its surroundings. That form of energy is called heat. A form of energy that helps set the direction of certain events is called potential energy. This snow is in a position to fall from where it rests. It has potential energy. Some of the sun's energy was converted into potential energy when water vapor was lifted up to form snow. Here in the mountains, snow still has some of that stored energy. If anything jars the snow loose, its potential energy will be converted into the energy of motion. This is energy of position decreasing through conversion to the energy of motion and sound. Chemists deal with another kind of potential energy, chemical energy. But its behavior is governed by exactly the same law which governs the behavior of stored energy in an avalanche. Stored energy will not spontaneously increase any more than snow will move back up the mountain against gravity, without an immense application of more energy, or unless we reverse this film's direction. And it is this tendency for potential energy only to decrease that gives direction to many events. The same tendency can be seen in a mousetrap. The sun's energy, by way of food and human effort, is stored in the trap's spring. Releasing the catch allows this unstable system suddenly to decrease its potential energy through an increase in its energy of motion and sound. In the molecules of this black powder, atoms of nitrogen and iodine are combined in an unstable arrangement that gives the powder chemical energy, and the merest touch is enough to release it. In any molecule, atoms are held together by electrostatic forces. It takes energy to separate them. A molecule has low potential energy. Separated atoms have high potential energy that is released when they combine to form a new molecule. Electrical energy splits water into hydrogen and oxygen, whose molecules have more potential energy than the more complex molecules of water. The hydrogen can be made to recombine with oxygen with a sudden lowering of potential energy by its conversion to light and heat. That is what happened in the famous disaster of the hydrogen-filled dirigible, the Hindenburg. This fearful holocaust was caused when something triggered a sudden and explosive drop in potential energy as atoms of hydrogen and oxygen combined. The same kind of thing happens when wood burns. Complex molecules in wood are hit by oxygen molecules in the air. If heat speeds up the oxygen molecules, they hit the wood hard enough to break off groups of atoms. Some groups attract each other, which is the source of energy in fire. Their collision releases energy and rearranges atoms. These groups collide to form water, and to free a carbon atom to form smoke. Or if it collides with an oxygen molecule, it may form carbon dioxide and release more energy. That energy helps break up more wood molecules, causing more collisions and releasing still more energy, and the fire grows. Anyone can observe that the chemical reaction called burning proceeds in only one direction. That although all the necessary energy and material are present as flame, smoke, and ash, they do not combine to form a match. Chemists generalize such observations into a law that says potential energy tends to decrease. Only by reversing the film can we see a spontaneous increase in potential energy, as the energy of heat and light appear to be converted into the chemical energy that bonds the atoms of the match together. Potential energy, whatever its form, spontaneously runs only downhill. But energy is not the only factor giving direction to events and making the world irreversible. There is another, the degree of randomness or disorder, called entropy. In a waterfall, although there is a large predictable drop in potential energy, there is also a change in flow pattern, from the ordered flow at the top to a churning maelstrom at the bottom, a tremendous increase in random motion. This suggests another basic law of nature, that chaos, or entropy, tends to increase and is no more spontaneously reversible than this waterfall. Entropy is a natural consequence of probability. If these fish could disperse further, there is only a low probability that they would collect together like this. Open a passageway to another globe, and they assume a more random distribution. The molecules of this gas are all in motion, and here are collected into one globe, a relatively ordered arrangement. But open the passageway, and the motion of the gas molecules carries them into another globe as well, until they reach the most probable arrangement, random distribution throughout the whole system. Two liquids, completely separated, is a highly ordered arrangement of their molecules. If allowed to mix, they do, producing a more disordered arrangement, a higher entropy. But in our irreversible world, two liquids cannot decrease their disorder by spontaneously separating. The entropy of billiard balls can be increased by the cue ball, but a spontaneous decrease in chaos looks suspiciously false. It is entropy that gives direction to time. With no noticeable change in entropy, it is hard to say if time here is apparently running forwards or backwards. But once it is possible to observe a change in the degree of randomness, it is immediately evident whether this is the reality of time or the fantasy of reversed film. The law of increasing entropy can be used to predict the direction of two kinds of change: chemical, or as here, physical change. As ice melts, its structure goes from the rigid order of crystals to the molecular disorder of a liquid, a predicted and observed increase in entropy. But water also freezes spontaneously if the temperature is low enough. Such an apparent contradiction can be explained by looking closely at a chemical change. This reaction at the interface between two liquids produces nylon, a synthetic material made up of long-chain molecules. There are actually two factors that can affect the direction of a change: potential energy and entropy. Sometimes these factors work against each other, as in the manufacture of nylon or other plastics. The general tendency is for complex structures to break down into simpler ones, an increase in entropy. But here, simple molecules are aligned and bonded together to form complex units. In order to compensate for this decrease in disorder, there must be a predominant lowering of potential energy. The great release of heat during the manufacture of these nylon products is evidence of the predicted decrease in potential energy. In this experiment, there is an unexpected increase in potential energy through absorption of heat, which is caused by a large increase in entropy. A film of water can show how much heat is absorbed. As ammonium nitrate is dissolved by water in the beaker, its orderly crystalline structure is broken down. That is the big increase in entropy that drives potential energy up instead of down. It causes so much heat to be absorbed from the surroundings that the film of water under the beaker freezes the glass to the wood. Throughout nature, there is another basic law, that no matter what happens locally, the total entropy of the universe must increase. A city is a local contradiction of entropy's general trend, because it takes simple raw materials and structures them into complex objects and arrangements. However, creating and maintaining urban order involves the use of energy, which is ultimately leaked off into the surroundings in the form of heat. Heat increases the random motion of air molecules, thus raising the level of entropy around a city. This compensates for the city's internal decrease in disorder, and the universal law is satisfied. The two universal laws, that total energy is constant and that total entropy must increase, help us understand the workings of nature, and also explain why no perpetual motion device has ever been built by nature or by man. Consider a hydro dam, a man-made waterfall for converting potential energy first into the energy of motion and then into electricity. There is some loss of the usable energy in the form of heat due to friction, but all energy accounted for. But what if we were short of running water? Could we take part of the electricity produced here and use it to keep up the water supply, with an electrical pump to take the water back up to the top? Could we in fact turn the hydro dam into a perpetual motion machine? No. The first law tells us we can't get more out of a system than we put into it. If we draw any electricity for other uses, there wouldn't be enough left to pump the full amount of water back up, and eventually the whole system would stop operating. The second law tells us that no matter what we did, all the usable energy will ultimately be used to overcome friction. Eventually, all the energy would end up as entropy in the random molecular motion of heat. Every system satisfies the universal laws of energy and entropy, even life itself, which is another localized reversal of the general entropy trend. Green plants absorb the sun's energy and use it to build complex substances out of such simple materials as water and carbon dioxide. These same materials are returned to the environment when an animal eats, and the food is broken down and burned up in the body to release the energy that sustains life. However, much of that energy is lost to the surroundings in the form of body heat. Thus, a plant eater, in using energy that originally came from the sun, releases much of it as heat and stores only a fraction of it in the chemical bonds within its body. That fraction of solar energy is all that is available in the food of meat eaters. But nowhere along the food chain is energy destroyed. Any form of life in its lifetime helps to balance the total energy budget and partially satisfies the general entropy trend. Even though the body also builds simple molecules into complex ones, all life processes produce heat. As in this horse race, the body heat escapes into the atmosphere. Students of the chemistry of the human body can detect just how much energy goes into the production of life's complex molecules, and how much is wasted by being leaked off into the surroundings. In this unique film, thanks to the work of Drs. Motoyuki and Rokuro Hayashi, we witness from within the human body what mankind has never seen before. The creation of a new human life. A mature egg cell in the ovary is about to burst free and float down into the womb. Sperm move towards where the egg now lies. Then, the moment when cells of male and female meet. From that instant, a new individual exists. The single cell begins to divide. The embryo grows more complex according to the detailed construction plan that exists chemically coded in its genetic material. The embryonic spine and the heart already pumping blood to help sustain life. Every life must eventually pay the final installment of its contribution to an increase in universal entropy, as death sets off the disintegration of the ordered structure of living tissue. In the end, decay bacteria feed on what was once alive, breaking down complex substances, releasing the components along with heat into the environment, complying with the laws of energy and entropy. If death is the inevitable end of life, What does the entropy law tell us of the ultimate fate of the universe? It is the sun's energy that powers the movement of water that man has learned to harness. Natural energy lifts water into the atmosphere and rains it down onto the earth. Energy is constantly converted from one form to another, but could the whole process ever stop? Yes, according to some. If the universal entropy law is accepted to its logical conclusion, at some incredibly distant point in the future, the sum total of all energy conversions will have leaked so much heat into the universe that everything will be at a uniform temperature. Then no energy will flow, and nothing will be able to happen in what is called the heat death of the universe. Others maintain that the whole process may at some point flip back to its beginning. Does time have an ending or a beginning? Or is all creation some infinitely repeating process, just as life repeats itself with every new generation? Will the universe be seeded with new galaxies of stars, more myriad than sperm? Will any supernova bursting into being ever be the last? Will life be endlessly renewed in an infinite cycle of generations? What chemistry has revealed of our irreversible world may help man's quest for knowledge about life, about time, and about the universe itself.